So, if you ask a spreadsheet to calculate the average income of an American, it will process the data, crunch the numbers, and confidently tell you the answer is $26,093.
Right, mathematically flawless.
Exactly. But the actual real-world national average is $30,861.
Which is a huge difference.
A discrepancy of nearly $5,000. The math was executed perfectly, the formula worked. And yet, the result is entirely wrong about reality.
Yeah, the spreadsheet doesn't know any better.
Welcome to this deep dive. Today, we are pulling excerpts from an open intro statistics textbook, and we're specifically looking at how we summarize numerical data.
And to be clear, our mission today is not to memorize formulas.
No, not at all. We are aiming for something much more practical here. We want to help you develop, X-ray vision for data.
I like that. X-ray vision.
Because numbers are the modern world's language. Whether you're prepping for a business meeting or just want to understand the news, you need to know how metrics can be perfectly accurate but still fundamentally deceptive.
You really have to spot the structural realities hidden beneath the numbers.
Okay, let's unpack this.
Yeah.
Let's start with the trap of the unweighted mean, which is exactly what causes that $5,000 income illusion.
Yeah, the mean, it's honestly the most common trap in data analysis. Because, well, the mean is our default tool for standardizing the world.
We just default to average for everything.
We do. We use means because they take messy, totally disconnected information and convert it into a baseline we can actually evaluate. The text uses this great example of Emilio's burrito food truck.
Oh, right, Emilio.
So over a 3-month period, Emilio makes $11,000, and he works 625 hours to do it.
Which is kind of an impossible metric to evaluate on its own. I mean, $11,000 sounds like a solid chunk of revenue.
It sounds great until you factor in the time.
Yeah, 625 hours over 3 months is a grinding schedule.
Right, so the raw numbers don't really tell a cohesive story there. But by dividing the revenue by the hours, you get a mean. Specifically, $17.60 an hour.
Suddenly it makes sense.
Exactly. He has transformed isolated data points into a standardized rate. That rate allows him to immediately benchmark his business viability.
He can compare it against a standard office job or minimum wage.
Precisely. The mean is a powerful standardizer. But the danger arises when we forget that standardizing data fundamentally strips away the original context.
And that loss of context is routinely weaponized. I mean, especially in marketing and research. The textbook brings up a trial for an asthma drug that illustrates this perfectly.
Oh, the asthma drug example is wild.
It really is. So the raw data showed that patients on the new experimental drug experienced 200 asthma attacks. Meanwhile, patients on the standard older drug experienced 300 attacks.
So if a pharmaceutical marketing department gets hold of those raw accounts, the headline basically writes itself.
Right. New drug reduces asthma attacks by 1/3.
But it's a complete structural illusion. It's caused by base rate neglect.
Because the text reveals the actual group sizes. Only 500 patients were given the new drug, while a full 1,000 patients were given the standard drug.
The denominator changes everything. The raw counts are completely meaningless without it.
When you calculate the mean, the truth actually emerges. The new drug resulted in 0.4 attacks per patient.
Right.
But the old drug resulted in only 0.3 attacks per patient. So the older drug is actually superior.
It really highlights how a classic case of imbalanced group sizes can distort raw counts. But the U.S. per capita income example you mentioned in the intro represents a more insidious trap.
Oh, the $26,000 figure?
Yeah, that one. It's an error of methodology, not just a missing denominator.
This is the one that really highlights the danger of the average. So if you pull a data set of all 3,142 counties in the United States, you have a list of per capita incomes for each county.
Right, a massive list of averages.
Exactly. And if you simply run an average on that list, you get that $26,000 figure.
Which is technically the mathematical mean of those 3,000 individual data points.
But it completely ignores the structural reality of the country. I mean, averaging a county of 5,000 people and a county of 5 million people together.
It doesn't work.
It's like weighing a mouse and an elephant, dividing by 2, and saying the average animal weight is exactly halfway between them. It completely ignores reality.
That's a great way to put it. The elephant makes up almost all the actual mass.
Just like Los Angeles or Cook County make up massive chunks of the actual population.
What's fascinating here is that this proves why critical thinking is absolutely required before simply accepting an average at face value.
You can't just blindly trust the math.
No, you can't. To find the true national average, you cannot just average the averages. You have to go back to the raw, unstandardized data.
So you have to add up the total personal income of every single individual in the country.
Exactly. Yeah. Add it all up and then divide by the total U.S. population. That gets you to the real $30,000 figure. The metric you choose really has to reflect the physical reality of the system you are measuring.
Which demands that we look beyond a single point of data. Knowing the center of the data, like the mean, is practically useless if you don't understand the shape and the spread of the data surrounding it.
And this is where data visualization shifts from being just a presentation tool to like an actual analytical tool.
Visualizing the truth.
Right. The textbook uses a data set called Loan 50. It's a sample of 50 loans plotted on a histogram.
Histograms are great because by grouping the loans into percentage bins, the graph instantly reveals the skew.
It gives you the shape.
Yeah, you see the vast majority of the loans are clustered heavily on the left side of the graph, right between 5 and 15% interest.
And then it trails off.
Exactly. The data trails off dramatically to the right, with just a few scattered loans way out in the 20 to 25% range. It's a heavy right skew.
That shape tells a bank risk manager vastly more than the mean interest rate ever could. I mean, it shows exactly where the core business lies and where the exceptions are.
Knowing the peaks is crucial.
Yeah, the text actually touches on modality, which is just the peaks in the data. They use this memorable, if slightly silly mnemonic.
Oh, the unicycles thing.
Yeah, so one prominent peak is unimodal. Think unicycles. Two peaks is bimodal. Think bicycles.
And they joke about waiting for the invention of the multicycle for anything with more than 2 peaks.
It's a bit cheesy, but it works.
It does. But beyond the joke, a bimodal distribution is a massive red flag in data analysis, right?
Oh, absolutely.
If you are looking at a histogram and you see 2 distinct peaks, it almost always means you have accidentally mixed 2 entirely different populations together.
Like mixing apples and oranges.
Exactly. Like if you chart the heights of a large group of adults, you'll get a bimodal shape because you're really looking at the distinct averages of men and women superimposed on each other.
That is the analytical takeaway there. The shape dictates the analysis.
Right.
But we also need a way to quantify that shape, specifically the spread.
How far things stretch out.
Right. We need to know the variance and the standard deviation.
Standard deviation is one of those metrics that constantly gets tossed around in corporate meetings to project authority, But its practical application is often totally misunderstood.
Yeah, people love to say it without knowing what it means. Mathematically, standard deviation is just measuring the typical distance of any given observation from the mean.
But practically, it establishes the boundaries of normalcy.
Exactly. A standard rule of thumb for roughly symmetric data is that about 70% of your observations will fall within one standard deviation of the mean.
And about 95% fall within 2.
Right.
That is the crucial concept for risk assessment. I always think of it like this. Let's say the average depth of a river is 3 feet.
Okay, 3 feet sounds fine.
Right. A mean of 3 feet sounds perfectly safe to wade across. But if the standard deviation of that river's depth is 5 feet, the situation is completely different.
Oh yeah, you're in trouble.
Exactly. The spread tells you there is extreme volatility. There might be a 10-foot drop-off hidden in that distribution that is going to drown you. You cannot survive on the mean alone.
You really can't.
You need the standard deviation to understand your exposure to those extreme outcomes.
And dealing with those extreme outcomes, like your 10-foot drop-offs, requires a different set of statistical tools entirely. Because when data becomes highly volatile, the mean and the standard deviation sort of lose their descriptive power.
They just get overwhelmed by the extremes.
They do.
Which introduces my absolute favorite visual diagnostic, the box plot.
Box plots are fantastic because they bypass the mean entirely. They're built on what we call robust statistics, starting with the median.
The exact middle.
Right. So if you rank all 50 loans in our data set from the lowest interest rate to the highest, the median is the value sitting at the exact 50% mark. Half the loans are cheaper, half are more expensive.
Then you build the box part of the plot to capture the interquartile range, or IQR, which represents the middle 50% of the data.
It's a great visual anchor.
Yeah, you are intentionally fencing off the core typical behavior, and then you draw the whiskers out to capture the remaining normal variance.
But what happens to the data points that fall outside those bounds?
Right, the text shows a loan with a staggering 26.3% interest rate floating way past the upper whisker.
That is an outlier.
Mm.
It is mathematically defined as an observation that sits an unusual distance from the rest of the data.
Okay, I want to push back on how these are handled in practice, though, because in a lot of corporate environments, cleaning data often just means deleting the outliers.
Yes, that happens a lot.
If I am trying to build a model of normal borrower behavior, isn't it more practical to just drop that 26% loan? Like, it's just a noise.
It's tempting to think that way.
The text specifically calls the median and the IQR robust statistics precisely because they ignore those extreme values. So why not just use robust stats to justify throwing out the weird data?
Well, because treating outliers purely as noise to be deleted is a massive analytical blind spot. Honestly, outliers are often the most valuable signal in the entire data set.
Really? More valuable than the core?
Often, yes. I mean, sure, sometimes an outlier is a literal data entry error, like someone accidentally typed an extra zero.
Right, a typo.
But a 26% interest rate is not a typo. It is a structural reality for a specific borrower. That outlier might reveal a systemic failure in your underwriting process.
Oh, wow.
Or conversely, it might reveal an entirely new, highly profitable risk demographic you haven't even explored yet.
So using robust statistics isn't an excuse to ignore outliers. It's actually a way to prevent the outliers from destroying your understanding of the baseline while still keeping them visible.
Precisely. Let's look at the Facebook Friends example from the
Okay,
text.
this is a great one.
The data indicates that 50% of Facebook users have 100 or fewer friends. So the median is 100.
But the mean, the average friend count, is 190.
Right. The mean is nearly double the median
How does that happen?
because the mean is heavily skewed by a very small population of super users who have thousands of friends.
Ah, right. The influencer's dragging the average up.
Exactly. So if you are an infrastructure engineer at Facebook calculating server load or an advertiser calculating total network reach, the mean of 190 is the metric you need.
Because it captures the aggregate volume.
Yes, but if you are a product manager trying to design the interface for a typical user, building around a mean of 190 will result in a product that feels overwhelming to the majority of your user base.
Because most people only have 100 friends.
Exactly. The median tells the story of the typical human experience. The mean tells the story of the system's total capacity.
This raises an important question, though. What happens when the data is so incredibly skewed that even robust statistics struggle to capture the full picture?
When things get really extreme.
Yeah, like if we try to plot the populations of all 3,000 plus U.S. counties on a standard histogram, a box plot isn't going to save us.
No, it really won't. The skew is just too extreme.
Most counties are pretty small, right?
Right. The vast majority of counties have relatively small populations, so they all cram into the very first lowest bin of the histogram.
Just a giant spike at the beginning.
Exactly. But then you have these massive megalopolises like Los Angeles extending the x-axis out to 10 million.
Mhm.
The resulting graph is just one massive spike on the left and a whole lot of empty space stretching to the right.
It renders the visualization totally useless. You completely lose the ability to differentiate between a county of 10,000 people and a county of 50,000 people because they are effectively compressed into the exact same visual pixel.
Which is why the textbook introduces data transformation, specifically the log10 transformation.
Changing the lens entirely.
Right. We apply a logarithmic scale to the population data.
Here's where it gets really interesting. Does performing a log transformation on the data border on manipulation?
Manipulation. How so?
Well, because we are fundamentally altering the numbers we're charting. We're changing the math to make the graph look better.
I see what you mean, but no. We aren't altering the underlying reality. We're just altering the scale to match the nature of the data.
Okay, explain that.
So, a log10 transformation converts the data into powers of 10. A population of 10,000 becomes a 4, because 10 to the fourth power is 10,000.
Right.
And a population of 1 million becomes a 6.
So instead of moving linearly, like adding one person at a time, the scale moves multiplicatively.
Exactly. When you are dealing with population dynamics, growth is often exponential, not linear. A log transformation pulls in those massive long right tails so we can analyze the data based on orders of magnitude.
It shrinks the extremes down so we can see the middle.
Yes. And the text proves how vital this is. When they plot county population against population change using the raw numbers, The scatter plot is just a dense, completely unreadable blob.
Just a mess of dots.
But when they apply the log transformation, a clear positive association suddenly materializes.
The hidden pattern.
Exactly. The structural relationship was there all along. It was just hidden by the extreme scale of the raw numbers.
We have to choose the mathematical lens that matches the structural reality of the phenomenon, and the text provides one final lens that completely abandons traditional axes in favor of spatial reality.
Oh, intensity maps.
Yes, intensity maps, because when data is tied to geography, stripping away the location data to put it on a scatter plot destroys a massive amount of embedded context.
You lose the where, which is often the most important part.
Right. The text utilizes intensity maps to plot poverty rates across the United States. Instead of dots on a grid, you see the actual map of the country, with colors indicating the severity of the variable.
It makes it so much more tangible.
It really does. And the authors impartially report what the data reveals here. There are distinct geographic clusters of high poverty.
The maps show deep concentrations in very specific areas.
Yeah, specifically in the southern states, the Mississippi floodplains, and parts of the Southwest.
And what's really compelling is that the authors place that poverty map directly next to an intensity map tracking the unemployment rate.
Which allows for an immediate spatial comparison. You can literally just look back and forth.
Exactly. The authors observe that while the maps share similar geographic patterns, like areas with high unemployment frequently overlap with areas of high poverty, there is a distinct difference in the base rates.
The intensity of the colors.
Right. The textbook specifically points out that the poverty rate is noticeably higher overall than the unemployment rate in these overlapping regions.
That is a remarkable observation to pull from a statistical summary, just by comparing two maps.
If we connect this to the bigger picture, the authors are using an intensity map to illuminate a really complex socioeconomic structure.
Because it's not just numbers, it's people's lives.
Exactly. The overlap, paired with the higher base rate of poverty, suggests a structural reality where a significant portion of the population is employed. They literally do not register on the unemployment map, yet their income still falls below the poverty threshold.
Wow. You would be incredibly hard-pressed to spot that nuanced relationship in a spreadsheet of raw variances and means. It really requires the geographic lens to make the numerical data legible as a human phenomenon.
Which brings us back to the ultimate utility of summarizing numerical data in the first place.
So what does this all mean for you? Navigating an environment that is just saturated with metrics.
It means you have to be vigilant.
Exactly. It means you now have the conceptual toolkit to defend yourself against misleading math. When a politician or an executive presents an average, to ask if they are citing a mean that's being dragged upward by massive outliers or a median that reflects the typical experience.
You know the difference now.
Right. And when you see a chart showing a massive spike in a single metric, you know to look for the standard deviation. You have to understand if that spike is a true anomaly or just normal volatility.
Drown in the river.
Exactly. Watch out for the 10-foot drop-offs. You understand that bimodal distributions often hide mixed populations and that log transformations can reveal hidden exponential trends. You aren't just taking numbers at face value anymore. You are analyzing the underlying architecture of the claims being made.
And as you apply these tools, consider this final thought, which extends kind of beyond the basic formulas in the textbook. We have spent this deep dive exploring how to accurately measure and summarize the world.
Right.
But consider the feedback loop this creates. What happens when a specific statistical summary, perhaps a robust median or a highly optimized mean, transitions from being a simple measurement into an actual target for a corporation or a government?
Oh, that's interesting.
Right. By choosing the specific mathematical lens through which we summarize reality, do we inevitably alter the very human behavior we were initially just trying to measure?